ฮัลโหลเทสฮัลโหลเทสฮัลโหลเทสฮัลโหลเทสฮัลโหลเทสฮัลโหลเทสฮัลโหลเทสฮัลโหลเทสฮัลโหลเทสฮัลโหลเทสฮัลโหลเทสฮัลโหลเทสฮัลโหลเทสฮัลโหลเทสฮัลโหลเทสฮัลโหลเทสเทสฮัลโหลเทสฮัลโหลเทสฮัลโหลเทส Hello, good afternoon. Just a moment. I would like to prepare for some video a little bit. Okay. So, let's see about last week. What have we already discussed from last time? So, last time I start a new lecture, nanotechnology, and I already tell you that the content, the content of this lecture. This lecture is lecture number 5. Yeah. This lecture, the content of this lecture consists of the overview, nanotechnology, and nanometal, nanoceramic, nanocarbon, nanopolymer, and nanobiomaterials. Yeah. On the topic, yeah, nanometal, nanoceramic, and so on. Yeah, this is nanomaterials. Yeah, and today we will continue from last time. Last time I show you that the nanotechnology development. Yeah, I present you the narratives of how the developments continue by showing the Nobel Prize. Yeah, in the field of nanotechnology or the related field. Yeah. And we have come to the award that given to the people who discover how to see small things like atoms. Yeah. Professor Kat Binnick and Eric Roher, yeah, who discover and develop the tools, yeah, for us to look at the atoms. Yeah. And this is the first time that we can uh, we are able to see just a small thing, yeah, in the nanoscale level. Yeah. So I think this slide is the last one, yeah, that I show you all and show the video. Yeah. So yeah, let's continue from here. Yeah. So the Nobel Prize, yeah, was given, yeah, in the 1986. Yeah, and in 1986 there was one moment, yeah, one important moment for nanotechnology. Yeah, because this year, Eric Drexler, yeah, who is very famous guy, and he is the one who promote the terms nanotechnology. And later on, yeah, after his outspeak uh, to speak loudly about the importance of nanotechnology, the United States later, yeah, under the president, uh, under the President Bill Clinton, yeah, he issued a very important act, that National Nanotechnology Initiative Act, yeah, at the time, yeah, and this law, yeah, they feed a lot of money, yeah, into the nanotechnology area, yeah, and from that moment it made America the very leader, uh, leadership, yeah, in this field. Yeah. So at the time of 1986, yeah, Eric Drexler author very important books called Engine of Creation. Yeah. And this book explain uh, how the engineering at macro scale, yeah, engineering concept like gear, bearing, yeah, and movable part, yeah, can be miniaturized into the down to the atomic level. So he proposed many interesting concepts like molecular gear, yeah, molecular bearing, yeah, and This inspire a lot of scientists, and it gives a very important question: can we create such a uh, small device like that? Molecular device, molecular engine. Could we create that? And as you see from 1986, is today 2025, is almost 40 years, from the time, from that time we still could not demonstrate this molecular gear. At the time I read this book. I was very excited about that. And I strongly believe we could do that. In 20 years. But today is 39 years. That from the time of the launch of this book. We have not yet even close to that capability. Uh, Nevertheless, we have achieved a lot of advancement, in this concept. We have we could not create molecular gear like this bearing. We, we we have not yet success, in that realm. Uh, but we have already come close to the concept, like molecular shuttle, and what I will show you later. In 1987, Professor Chong Marie, he received Nobel Prize in Chemistry for the introduction of the supramolecular chemistry. He create, he developed a method to synthesize supramolecule. Supra it means bigger. Because of chemistry in the past, when they synthesize molecule, it mostly small molecule. Or if it create very big molecule like polymer, it must have a repeating unit. It means even you create a bigger molecule like polymer, but it's the repeating of similar it's repeating of exactly same unit. But you repeat it many times, it create polymer. It's bigger, but the monomer that is a building block of the polymer is still very simple. Supramolecule have complexity. You create bigger molecule, and it has complexity inside that. Normally, when you chemistry at about 50 years ago or 60 years ago, when they developed or synthesized a molecule of 50 or 60 atom, non-hydrogen, non-hydrogen 60 atom already very big. At the time, it's not easy for them. But Chong Marie, he showed that we could achieve capability, create 100, 200 non-hydrogen supramolecule, bigger molecule. So he changed the paradigm of chemistry, and this paradigm would later lead to the development of molecular shuttle, molecular gear, molecular engine, under the concept of Eric Drexler. So later on, after 1986, 9 years, no development, no big development in nanotechnology. And in 1996, Nobel Prize was given to Richard Smalley, who discovered nanocarbon. Especially he at the time the carbon 60, or the buckyball, was very famous. Why the this Nobel Prize is very important because this is the first time that we as human could create the carbon form that you know that the carbon atom is everywhere. It's inside a lot of organic materials. And pure carbon, whenever you see the pure form of carbon, there are actually about three types of carbon that can form three form of carbon. The first one is amorphous carbon, like the charcoal. Secondly is diamond. Diamond is a pure form of carbon. Very strong material. And another form of carbon is the graphite. The typical materials in the pencil. And Richard Smalley, he showed that carbon could form into small molecule like carbon 60. It's a pure form of carbon, no other elements. Just one type of elements, only carbon. And actually, it's unfortunately, the discoverer of carbon nanotubes, Sumio Aishima, he did not receive the Nobel Prize. Because I think it's important because the carbon nanotube also a form, a new form of carbon too. But unfortunately, he has not received that Nobel Prize. In 1997, the Nobel Prize was given to Stephen Chu, professor at Stanford University. He developed method to cool and trap atom. You see, normally atom on-way moves. It moves on the times. You cannot see atom that stands still. You cannot see atom that just don't move. Every atom move. It move, it vibrate, it rotate. It always change location. It's very difficult to make atom stop moving. So even you cool down the temperature, near zero temperature or 0 Kelvin, atom still moving. So Stephen Chu, he developed method to cool down the atom, to stop atom from moving, trap atom. He used the light. He used laser light, laser beam. If you have an atom here and the atom move on the north direction, you shoot with the light, laser light. Then the atom move back to the south. Then you shoot with the laser light. If atom move on the west, you shoot atom. If it move to the east, you shoot atom. You shoot atom from many directions. Finally, atom cannot move anywhere. It's just trapped inside. So this is a way that atom can be trapped. So Stephen Chu, he was very famous professor, because he is the first professor that later become the Minister of Energy, Department of Energy. He become the Minister. I am not sure that he become minister under Bill Clinton, I think. Let me check. Stephen Chu. Stephen Chu. Minister of Energy. Secretary of Energy. Barack Obama. He become he become later the Minister of Secretary of Energy, the Department of Energy, and Elon Musk should thank to him because the policy of Stephen Chu, he promote green energy. He want to promote the electric vehicle. And Tesla was founded by Elon Musk to exploit this policy. So 1 year later, Nobel Prize in Chemistry was given to Walter Kohn and John A. Pope. They developed the quantum computational method that allows prediction of structure and property of nanomaterials. So the importance of this discovery is that with discovery, it means you can predict nature, very small world of molecule and atom, using this mathematics and computational algorithm. You can design, molecule. You can connect atom with each other, and then you can predict the physical property, chemical property using mathematics. Imagine you want to create new materials. You just put atom together. Put atom. Then you predict it. You predict how the property should be, even before you synthesize or have the real molecule. So this is very important. You can create a lot of molecule before even having the real one. This method is called molecular modeling, molecular design, molecular simulation. And with this, you can create a design. You can design drug in advance to fight virus, to fight with disease. Antibacterial drug, for example. You can, and even you can use a virtual reality software to dive into the small world, to move the atom, try to rotate the molecule and see how molecular property would work. So with this, you can simulate the small world. Okay, let me show you. Let me show you some good video to show this concept. So I will not create. I will not make it full screen to avoid copyright. I think I can channel they have very serious copyright. So I would like to ask Lycan channel. I play this video for my student. Please allow me to show this video to the student. So I am thankful to Lycan channel for giving me the right to show this video to student. You see that? Okay, I show you this. I show you the subtitle. So okay, you will see that this is on atom. Yeah, they show that a lot of atom here, and this is in the cell. Yeah, yeah. If they show water molecule, in the cell there are a lot of water molecule. If they show water molecule, you cannot see you cannot see water molecule, yeah, because in our cell filled with water. Yeah, water filled everywhere. Yeah, that's why in the simulation they they include the water molecule there, but they don't show it, they don't display it, so that you can see the organ inside the cell. Yeah, the molecule, outer molecule inside the cell. Yeah, yeah. This is a cytoplasm in the cell, and everything move. You see, atom move. Yeah, ribosome. This is the ribosome. You know that the ribosome is a molecular device that synthesize protein. Yeah, yeah. This is the ribosome molecule. Yeah, they synthesize the protein, yeah, by interpreting the code from DNA. Yeah. Yeah. Here they show the this is the ATP. Yeah. Every everything moving very fast, yeah, inside your cell. Okay, I show you. You can later you can look at this video by yourself. Yeah, I don't want to play the full version. Yeah, in order to not to violate the copyright. So thank you very much for liking channel to allow me to show to the student part of the video. Yeah, okay. So another later on, yeah, another Nobel Prize was given to the discoverer of the conductive plastic or conductive polymer. Yeah. Imagine 30 years ago, 40 years ago, when we talk about plastic, normally we mean, yeah, some material that are dumb, yeah, some material that have only physical property to maintain shape. Yeah. When you talk about plastic, you think about the bag. Yeah. You think about the cup. You think about container. Yeah. And we use this material for maintaining shape. Yeah. We use material to this material. Yeah. In not the smart way. Yeah. But these three scientists change our concept about plastic forever. Yeah. Nowadays, conductive plastic are in smartphone, in smart TV, in electronic display. Yeah. So it even can produce lighting. Yeah. For you. Yeah. So they change the concept for plastic forever. Yeah. Plastic now become intelligent and smart materials. Yeah. So what they discovered that plastic can conduct electricity. Yeah. Yeah. It has never been before. Yeah. That when we talk about plastic, it means insulator. Yeah. Plastic could not. Yeah. At the time, plastic should not conduct electricity, but these three scientists prove that plastic can do it, can do that. And the conduction band is formed by a network of double bond. So conductive plastic or conducting polymer, they have a network of double bond, and this double bond form a kind of conjugation. Electron can flow. You see, this is double bond, single bond, double bond, single bond. It's alternating along the polymer chain. So nowadays, you have a lot of device that made from conductive plastic, like uni- because plastic is flexible, and it can be very thin. So you can make the device display a device that can be flexible. You can have electronic that are flexible and thin. For example, here this is a display. This is a kind of electronic paper, electronic skin, and foldable solar cell, flexible solar cell here. So I would come back to this topic later. When later we will talk about the nano polymer. And in the year 2003, the Nobel Prize was given to Peter Acker and Roderick McKinnon, who discovered the small, ultra small machine that can control the entrance, the entry of molecule and ion into cell that regulate these molecular gate molecular machine that close and open to allow the mobilization of ion and small molecule. It control your cell to allow something to move in and move out. So this is important for me in the Nobel Prize in Physiology in the year 2004. Nobel Prize was given to Linda Buck and Richard Axel, who discovered the sense of smell. How smell work. How the sense of smell in your nose work. And from this inspiration, I founded my startup company, digitalization of smell, called MUI Robotics nowadays. So thanks to Professor Richard Axel and Linda Buck for your discovery that inspired me to develop this technology and this startup. So I have video to show you. The sense of smell is for human is so complex. Even nowadays, artificial intelligence still don't have comparable sense of smell like human. Very complicated. So I show you the video how the sense of smell works.
Le nez du vin. Let's take a look at the mechanisms that allow us to perceive, identify, and memorize smells and aromas. Let's begin with a definition. Smells and aromas are volatile molecules. A glass of wine contains a great many volatile molecules. We detect these molecules in two ways: with the nose, when we call them smells; through the mouth, when we call them aromas. Both of these pathways lead to one organ found at the top of the nasal cavities, the olfactory epithelium. This mucous membrane is covered with cilia. The cilia have olfactory receptors, which capture odoriferous molecules following a lock and key system. We have 400 different types of olfactory receptors. Each one recognizes only a small part of an odor molecule. It therefore takes several receptors to identify just one molecule. Through the accumulation of combinations, humans can thus potentially detect 1 trillion smells. Let us continue on our olfactory journey. Each receptor activates a different area of the olfactory bulb, located between our eyes. When a molecule connects with several receptors, it activates different areas of the bulb. The activated areas form a specific, unique olfactory map. When we taste wine, the map that forms on the olfactory bulb results from perceiving dozens of volatile molecules in the wine. This complex map corresponds to the overall scent of the wine, its bouquet. Only by practicing and giving our nose olfactory training can we pinpoint smells we recognize in this complex map. This is why it is important to have as many maps as possible memorized in order to be able to deconstruct a bouquet and identify the many aromas that a wine contains. The aromas of Le Nez du Vin are an olfactory alphabet. By memorizing them, you learn the language of wine speak so that you can share impressions with fellow wine lovers.
Oh, sorry, I uh, forget to uh, turn on the microphone. So, okay, I repeat that a little bit. Yeah. Uh, the Nobel Prize in 2010, yeah, was given to Kam and Novoselov. Yeah, these two duo, they are professor and PhD student in the lab. Yeah, very nice story. Yeah, that professor and student received Nobel Prize together. Yeah, I show you the video how they discover this. Yeah, uh, they discovery graphene by extracting layer of graphite repeatedly using Scotch tape. Yeah, very easy method. Yeah, they have you see this is the graphite and this is Scotch tape. They use Scotch tape, yeah, to draw out layer of graphene until For example, if you start with 100 layer, you do it repeatedly many times to draw out the layer of graphene using the Scotch tape. Finally, you yield the single graphene layer, and they show experimentally that they can finally they can extract single graphene layer for the first time. So that's why they received the Nobel Prize. I show you the video.
Picture this. You were thrown into a dingy room and told you can't leave until you have created the thinnest material known to man. Not only that, it must also be the strongest, the best thermal conductor, and as good at conducting electricity as copper. I know, it sounds hopeless. But luckily, you know something about nanotechnology. You know, really tiny devices and materials that are less than 100 nanometers in size. Of course, I don't have to tell you, a nanometer is a billionth of a meter. That's roughly the size of 10 atoms. But how do you create something that tiny? It's time to embrace your inner MacGyver. You're going to need a pencil, some Scotch tape, and a healthy dose of elbow grease.
Now they will show you how to extract graphene from graphite. You know, in the pencil there are graphite.
A pencil contains not lead, but graphite, which consists of sheets of carbon in a hexagonal lattice. When you write, layers of graphite slide off the tip of the pencil and stick to the paper. Usually many layers...
That's how you use pencil. Yeah, when you use a pencil, the graphite layer peel out, and remain on the paper, and you see the black on the paper.
Are stacked on top of each other, but once in a while you get a single layer of carbon atoms, and this is called graphene. In 2004, Andrei Game and Konstantin Novoselov created graphene using nothing but graphite and Scotch tape. They placed a graphite flake onto the tape, folded...
This is they use Scotch tape, put on the graphite, and then the graphite will be on the Scotch tape. And you use another side of graphite, the screen, to draw the graphite out.
Put it in two and then cleave the flake in half.
You see?
They repeated this procedure a number of times and then studied the resulting fragments. To their astonishment, they found some of the pieces...
You repeat many times until it's thinner, and remain only single layer.
...were only a single atom thick. This was particularly unexpected because it was thought a single layer of graphite would not be chemically stable, especially at room temperature. Graphene conducts electrons faster than any other substance at room temperature. This is because of the extraordinarily high quality of the graphene lattice. Scientists are yet to find a single atom out of place in graphene. Since the electrons aren't scattered by defects in the lattice, they go so fast that Einstein's relativity must be used to understand their motion. And this perfect lattice is created by the very strong yet flexible bonds between carbon atoms, making the substance bendable, but harder than diamond.
Graphene very fantastic. The graphene is hard like diamond, but it's bendable.
Graphene is incredibly strong. If you could balance an elephant on a pencil and support the pencil on graphene, the graphene wouldn't...
It is so strong that it can sustain the elephant on its sheet, single sheet. Very strong, fantastic.
Break. Of course, the pencil would. For their discovery, Game and Novoselov were awarded the Nobel Prize for Physics in 2010. And this is only the beginning for graphene. Scientists are hard at work exploiting its unique properties to create thin, transparent, flexible touchscreens, smaller, faster, more energy efficient computers, tough composite materials, and more efficient solar cells. And now consider, this is only
Okay. So another important one I will show on you also the video is the three scientists, Japanese scientists who discover the blue LED, Professor Akasaki, Amano, and Nakamura, especially the most light, picture here. Professor Nakamura, he has a very interesting story, because he start his laboratory in very small laboratory in a remote province of Japan. Very in a small company that incredible to find to develop this technology. Because other big company have more funding, have more have bigger lab, have better equipment, but could not discover the blue LED. Why the blue LED is important? Because at the time before the year 2000, we already have two color of LED, the red one and the green one. You can see that in most electrical appliance in the past, they use only red LED, and later they use green LED. But if you don't have a blue color LED, you cannot produce the full color. Because the full color, if you want to generate the true color, the full color display, like television, TV, smartphone, you need the blue color. Red color and green color is not enough. You need the blue color, and blue color is difficult to produce. And with the blue color, when you can mix red, green, blue, and you can create the white color. That is very important, because you can create the lamp, you can create the white light. That's very important to make lighting cheaper, energy saving. So I show you the video, how blue LED change the world.
Smartphones, TVs, computers, iPads, and many other modern miracles are made possible by power-efficient.
Okay, I would like to ask the Bloomberg to allow me to show this video to my student. Please allow me to show this for education only. I don't use it for commercial. I use this for educational purpose. Bloomberg, please allow me to play this video for my student online. Thank you.
LED screens, but the real impact goes well beyond our brightly lit gadgets. Lighting accounts for 20 to 30% of global electricity consumption and about 6% of greenhouse gas emissions. Given that LED bulbs use around 80% less energy and last 25 times longer than incandescent lighting, they have the greatest potential impact on energy savings globally. But when the first LEDs were introduced in the 1960s, they didn't have much use. It wasn't until the 90s when Japanese scientists discovered the missing link needed.
You see, they have red, they have green, but still don't have blue color.
A spectrum, the blue LED. Here's how the color blue changed lighting.
For the red and the green, no Nobel Prize, but for the blue, it's important. lighting is impossible if you don't have blue LED. Yeah.
After Thomas Edison invented the light bulb in 1879, incandescent lights lit much of the 20th century. The problem is they waste a lot of energy, lost in the form of heat, and they don't last long. Fluorescent lights started being used in the 1930s. Although much more efficient than incandescent, they're not an ideal replacement. They contain toxic mercury, age significantly if they're frequently switched on and off, and are prone to flicker. There needed to be a better solution. In 1961, Gary Pittman and James R. Beard of Texas Instruments accidentally invented the first practical light-emitting diode while trying to make a laser diode. The first LEDs emitted infrared light, invisible to the human eye, which later became useful in things like remote controls. And for the next 3 decades, advances were made to include red and green, but they couldn't quite get to blue, which was needed to make white light. But the appeal was obvious. Unlike ordinary incandescent bulbs, LEDs don't have a filament that will burn out. They don't get hot, and they require a lot less energy. So the biggest electronics companies raced to create a powerful blue LED.
Okay, because this is quite a long video, I will go fast forward. Yeah, okay. Later, Professor Nakamura, yeah, he worked in the
This led a scientist from a small chemical company in Japan.
and
Firstly, by virtue of having little to no budget, scientist Shuji Nakamura was forced to create red and infrared LEDs from scratch,
so
using parts he scavenged.
He has to start from scratch, yeah, by buying a second-hand machine, yeah, and try different way to produce the material that can create the blue LED, yeah, differently from other big company. Yeah. And it took him around 10 years, yeah, before he find a way, yeah, to make it emitting blue light. Yeah. And he used gallium nitride, yeah, the material that other company don't want to do it.
Blue light would make it much easier for him to get the necessary papers published for his degree. Again, he went back to the lab, not taking holidays and not varying his daily routine. But this time was different. He convinced Nichia to buy the equipment for manufacturing LED material. Instead of starting from scratch, he made small modifications to the commercially available equipment. His extensive experience building red and infrared LEDs aided the alterations. Just over a year later, Nakamura made his first successful growth of gallium nitride. His method, called the two-flow MOCVD, is still used to this day. From this and discoveries of other Japanese scientists around that time, he was able to produce the first brightly shining blue LED. Nichia is still a leader in the LED industry, used by Apple and other electronics manufacturers. In 2014, Shuji Nakamura was awarded the Nobel Prize in Physics for his invention, along with 2 other Japanese scientists who developed high-quality gallium nitride materials prior to Nakamura's breakthrough.
You see?
The small, energy-efficient and extremely bright
Now
LEDs
they have a full color. Yeah, they have red, green, and blue. They can produce the white color.
started a light revolution and are now used in almost every piece of electronics.
So
Without it,
you have
much of what
the color you can
we use today wouldn't be possible. It
almost
also has
any
life-changing implications in the developing world.
Okay.
With LEDs, solar panels and small batteries are more than enough to power the homes of the 1.2 billion people who lack access to electricity.
So 1.2 billion people that have never used lighting before, yeah, because the LED is energy efficient method. Yeah, they need only a little amount of energy. That's why they help billions of people accepting lighting. Yeah.
Most of those people are still burning wood or gas for light, which is not only inefficient, it causes pollution. It's estimated that switching all lighting to LED would reduce annual carbon dioxide emissions by about the same amount as that produced by 3/4 of the cars in the US. That's a potentially bigger impact than wind or solar power. And with global warming due to human activity generating catastrophic
if all
effects on
house in the world use LED, it helps a lot to reserve energy and also to reduce the carbon emission. My house on on lighting on lamp are from LED already. Okay. Another important discovery. And you see that if you recall in 1986, Eric Drexler proposed the concept of molecular machine. And then in the year 2016, in the year 2016, Nobel Prize was given to 3 professors who developed real molecular machine. You see how different it is. The conceptual molecular machine is the miniaturization of engineering gear and bearing. But the real molecular machine look like this. But it takes 30 years that this concept become realized and become practical. Here they show the molecular shuttle. They can control a kind of ring here to move back and forth, like a molecular shuttle. And they even show the rotation of the molecule to show like a molecular chassis. Why molecular machine are important idea? Because our life run our body run by molecular machine inside our body. Protein, ribosome, and especially the division of the cell. As I will show you the video here. I will show you that the division of the cell here using the concept of molecular machine.
These are
You see, when the cell divide, it use
are tiny molecular machines, and they are doing this inside your body right now. To understand why, we have to zoom out. Every day in an adult human body, 50 to 70 billion of your cells.
I don't dare to play the full video to avoid the copyright infringement. So I suggest you to see the name of video here, your body molecular machine, and perhaps you can see it later by yourself. So I move. This is very interesting. This is a 6-minute video. They show that when the cell divide, this molecular machine will be used to pull out chromosome, the copy of chromosome, to different side, to the left and to the right side, and later the cell will divide with the same copy of DNA, of the same copy of chromosome, and this molecular machine pull, and they show how molecular machine work, to during the cell division. You study from high school, that when the cell divide from 1 into 2 cell, chromosome will arrange at the middle, and later it will make a copy, and after that the chromosome will be pulled by some small fiber to the left and to the right, to allow the cell division successfully, with exact copy of DNA. And I have this question from when I was a high school student, how this happened. And now I found the answer already, that it because the molecular machine that working to you see they did some the molecular machine pull out a part, and if we look we zoom in how they pull out, they use molecular machine to gradually move the chromosome, the whole molecule of the chromosome out.
Get ready to divide. The kinetochore also mechanically senses tension. When the tension is just right and the position and attachment are correct, all the proteins get ready, shown here by turning green. At this point, the stop signal broadcasting system is not switched off. Instead, it is literally carried away from the kinetochore down the microtubules by a dynein motor. That's the walking guy. This is really what it looks like. It has long legs so it can avoid obstacles and step over the kinesins, molecular motors that walk in the opposite direction.
Personally, I'm astounded by these tiny molecular machines, how they're able to routinely and faithfully execute their functions billions of times.
Okay. Please see in detail by yourself. Okay, and in the year 2017, Nobel Prize was given to 3 professors who developed the so-called cryo-electron microscopy that allow the microscope to look at 3-dimensional shape of virus or even protein or DNA molecule. If we go back to the Nobel Prize in 1986, see, this is for the discovery of electron microscope, 1986, and now it's in 2017, it's around 40 years, 30 years, it's around 30 years. That microscope has been developed to see smaller, to see smaller things. You see the electron microscope at the top. You can look at the head of the ant, and with 3 dimensions. But if you want to see smaller things like carbon nanotube, it can be only 2-dimensional. You have to use TEM. But with the new technology, combining the power of microchip, the power of algorithm mathematics, then you can create image of small things like the virus or protein and DNA. It can be it can generate a 3-dimensional picture of nanoscale object. Then look at the year 2018. This is the leverage of the technology that given by Professor. Just a moment. In 1997, Stephen Chu show how to stop atom, yeah, how to cool down the atom, yeah. And then in 2018, yeah, around 20 uh, on around 20 years later, yeah, they show how to manipulate manipulate object using light. You see, they can manipulate small object, using light. It called optical tweezer. Yeah. Yeah. It's a tweezer is a kind of equipment, yeah, that you can pick up things, yeah, manipulate things. Yeah. But this is nano tweezer. Yeah. Is you manipulate very small, yeah, small thing. Yeah. And if you make this bead, yeah, very small, yeah, and it attached to the protein, yeah, and when you use this bead, yeah, to you control with the uh, optical trap, yeah, you can pull the bead up and down, yeah, and then you can calculate the force being used, yeah, to cleave a protein or to make the protein elongate, to elongate the protein and so on. So it's the first time that we can measure the force in intermolecular force within the protein, yeah, within the molecule. Yeah. When you elongate the protein layer, yeah, you use the bead, you use this bead. Yeah. So so the force can be measured, yeah, for the first time. Yeah, that very valuable method, yeah, to understand the force inside big molecule. Yeah, and this knowledge could be used in many areas. Yeah, in the drug design, in the design of protein, design of enzyme. Yeah. So I play this video, yeah, that explain how
This year's Nobel Prize in Physics was
yeah, how molecular twister works. Yeah.
awarded to the following three people. But in this video, I'm going to talk about Arthur Ashkin's invention of optical tweezers. Optical tweezers are things that use a laser beam to physically hold and move microscopic objects. They can trap and manipulate small particles. But the question is how? Let us take this bad boy. This bad boy is a micron-sized dielectric particle, which means it is an insulator and can be polarized by an applied electric field. Let's put him in a laser beam. Diameter of this bad boy is significantly greater than the wavelength of light. If we place him in the middle of the beam, he is perfectly comfortable. But displacing him from the center will cause a net force to act on him toward the center. Apparently, he likes to stay in the denser part of the laser beam, and this is what traps him. Think of it this way. Our bad boy has some kind of shield, which he uses most effectively if he blocks the intense part of the beam. So he likes to stay in the center or his sides would get burned. But let's do some actual physics. This trapping can be explained using ray optics. Rays of light emitted from the laser will be refracted as it enters and exits this dielectric buoy. Because of this, ray will exit in the direction different from which it originated. Since light has a momentum associated with it, this change in direction indicates that its momentum has changed. Due to Newton's third law, there should be an equal and opposite force on the buoy. The particle has a net force returning it to the center of the trap because more intense beam imparts a larger momentum change toward the center of the trap. The net momentum change or force returns the particle to the trap center. But this traps our buoy in the center of the laser. For instance, in this case, it can still move up and down. We need a focus laser to keep the bead in a fixed axial position. This can be done using an objective lens. So now if this bead moves forward, the momentum change of the focus ray will cause a force toward the laser focus. So this boy will stay slightly behind the focus, where this force compensates the scattering force.
Okay. Yeah, and in 2021, yeah, the Nobel Prize was given to Papa Boutian and Julius. Yeah, he discovered the sense of touch and temperature. Yeah, that explain how you feel when you touch something. Yeah, your sensor in your skin, how it works. Yeah, and how you feel the cold and the hot weather. Yeah, is the mechanism in the sensor. Yeah. So now I continue, yeah, to the nanomaterials. Yeah, and we have five topic, yeah, to be discussed. Yeah, the first is the nanometal, yeah, nanoceramic. Yeah, these two, yeah, metal and nanoceramic. This is an inorganic material. Yeah, and for the nanocarbon, nanopolymer, and nanobiomaterial, these are organic materials. Yeah. You may have known already that inorganic and organic material, how different they are. Yeah. Organic materials are materials that consist in living organism. Yeah. In tree, in human, in bacteria. Yeah. Yeah. Organic materials. Yeah. And inorganic materials, they are materials that happen in nature, or it can be synthesized, but most of them, they are not uh, relevant, yeah, to the living organism. Yeah. So uh, yeah, firstly, I discuss about the nanometal. Yeah. When we talk about the nanometal, there are two nanometal that have been widely used and famously known. Yeah, there are silver and nanogold and nano silver. Yeah, sometimes for the nano silver, sometimes we call it silver nano. Yeah, you have you may have heard about it already. Yeah, because silver nano has a antibacterial property. Yeah, that you may already have a refrigerator that have this feature. Yeah, the silver nano cleaning system. Yeah. Okay, talk about the nano gold first. Yeah. For the gold have a uh, very interesting property. Yeah. When you look at the gold, yeah, the necklace or the bulky gold, yeah, the gold in the big size, you see the color is yellowish, uh, golden yellowish color. Yeah. But when gold become very small, yeah, when the size become at the nanometer level, yeah, like 100 nanometer or smaller, the color will change depending on the size. So the color become dependent on the size. If you have a big goal, yeah, bigger size of gold, like the the gold lot, the gold necklace, the gold ring, you see no matter how the size change, the color is yellow. Yeah. But when the size is very small like this, yeah, like 2 nanometer, 10 nanometer, 50 nanometer, 100 nanometer, the size change. Yeah. Why? Yeah. You see, smaller have red color, yeah, but the bigger has blue color. How it happened? Yeah. The color change. Yeah. You see how it happened. Yeah. And the uh, ancient people, they know how to use, yeah, how to use this property, yeah, to make a color. Yeah. They call it stained glass. Yeah. They they they, they produce the color in the church. You see, if you go to the Christian church, the Catholic church in Europe, yeah, and they usually have a stained glass at the side of the church. Yeah. When the sunlight passes through the church, you can see very bright color of red, blue, green, yellow, and so on. How this happened? Yeah. How the ancient people know to use this? Yeah. Actually, they might not understand nanotechnology. They might know it accidentally. Yeah. They by milling the gold down to small size of powder, and they might know that if you milling if you mill the gold down to small powder, then you can play with the color. Yeah, this is the ancient might have that intrinsic knowledge at the time. Yeah, they might not understand how it happened, but they know that they can how can they change the color. Yeah. So then this not only happen for the gold, it also work for the silver too. Yeah. For example, here for the gold, yeah, you see that if the size of the powder is 25 nanometer, yeah, it create the red color. Yeah. But if it 50 nanometer, it give green color. Yeah. 100 nanometer, it give yellow color. Yeah. For the silver, yeah, they discover that for the 100 nanometer is yellow. Yeah. 40 nanometer is the blue. Yeah. But here 100 nanometer the same size with this. Yeah. It's red. But because they change the shape. Yeah. So they can play with not only the size but also the shape. Yeah. So I show you the video. Yeah. This is the mystery of ancient technology that high tech. Yeah. And even today we to make the stained glass again is not easy. Yeah.
We live in a time where with a flick of our finger we can explore the world. We tend to forget that past civilizations had technologies we have only just begun to understand. The Lycurgus cup is a 4th century Roman glass cage cup made of a dichroic glass. Dichroic meaning it appears to be a different color depending on whether or not light is passing through it. The chalice is red when lit from behind and green when lit from the front. It is the only complete Roman glass object made from this type of glass. The change of color from green to red mimics the ripening of grapes, suitable to the chalice's theme. It depicts King Lycurgus of Thrace entangled in grapevines. The chalice's theme is based on the myth that he was punished for attacking Dionysus, the god of wine and merriment, and Ambrosia, one of his followers. It is not known whether or not the dichroic effect was deliberate or the fortunate result of accidental contamination in the molten glass. The optical illusion of this rare form of glass so delighted the Roman aristocracy that it attracted the attention of emperors. It was said that Emperor Hadrian sent a cup that changes color to his brother-in-law as a gift for his banquets. It must have seemed quite magical at the time. It was kept in an almost perfect state of preservation until it was acquired by the Rothschild family in the 1800s, then bought by the British Museum in 1958. For a long time scientists could not test the materials to determine why the color change was occurring. It wasn't until the 1990s that a group of scientists were able to explore some fragments of the glass and found small particles of silver and gold about 50 nanometers in diameter suspended in the glass. These metallic nanoparticles are the cause of the different colors observed. This is a one-of-a-kind object. There are a few other surviving fragments of Roman dichroic glass, but they vary considerably in their two colors. Corning Glass Works has now reproduced a blank of a similar material which under the right lighting display.
Now we could produce nano gold and nano silver, but you see that the colors still not beautiful like the ancient
Is
technology
the same Lycagus effect of green to red color change as the Lycagus cup. Cranberry glass or gold ruby glass is somewhat similar and far more common. It is manufactured with colloidal gold, but only ever shows a red color. So even today with all of our technology, this ancient nanotechnology is difficult to reproduce. As always, thanks for watching, and if you enjoyed this video, please like, comment and subscribe.
Okay, here you see the nano silver. Nano silver, if you make it as small as 20 nanometer, the color become black, and it has a antibacterial property, which means it can kill small organism, bacteria, fungi, virus. So that's why they use it. They like to use silver nano to with the cloth that normally produce bad smell, like underwear or sock. Because why when you sweat out liquid from your body, the sweat from your body come to the underwear, or the sock, and the bacteria eat the nutrient in the sweat and produce a volatile gas that has a bad smell. So if you have silver nano, embedded in the textile of the underground and the sock, it kills bacteria. So if the bacteria die, it could not produce bad smell. That's why silver nano are very useful. We can use also we can use silver nano also in refrigerator. That refrigerator that have a nano silver system, you will not feel the bad smell, or the fish smell, in the refrigerator. Okay, I will play video here.
When you're at the gym working hard, you don't get those gains without gaining a bit of sweaty stench too. Luckily, for the right price, clothing manufacturers offer a remedy. Supposedly stink-free exercise clothes that have silver nanoparticles embedded into the fabric. It sounds a bit gimmicky, but does it actually work? And if it does, how do we know that these particles don't come out in the wash? Your workout clothes, especially ones made of polyester, can trap both the bacteria that cause BO and the fatty acids from your skin that they feed on.
We smell bad because of our sweat, and our sweat release, and it feed the bacteria to grow.
It's a stinky little paradise, no matter how many detergent pods you chuck in there. Fortunately, humanity has known that silver kills bacteria for thousands of years longer than we've known what a bacterium is. Today, silver is used in everything from burn treatments to food storage and even medical devices. So yeah, it works. Silver is bad news for bacteria. There are multiple ways it can ruin a bacterium's day on a molecular level. Ultimately, silver stops a bacterial cell from performing very basic chemical processes needed for survival. Recent improvements in technology have allowed the scale of antibacterial silver to reach into the realm of nanotechnology. We're talking particles so small that you can fit thousands of them across the thinnest of human hairs. Not all of the methods used to attach silver to your workout shirts are nanotech in the strictest sense, but there's a thin line between nano and non-nano when it comes to silver. That's because silver has an interesting property where non-nano-sized particles releasing silver ions can generate nano-sized ones. So even though the word nano is a selling point for these kinds of products, silver is pretty much nano whether or not you meant for it to be. How tightly the silver is attached to the fabric seems to be more important than the size of the particles, both for killing bacteria and for the staying power of your fancy shirt. That's because you want the silver to stay there so it keeps killing bacteria after you wash it. Methods vary, from chemically bonding the silver directly to the polyester fiber of the garment.
The art of the silver nano working is that how can you embed the silver nano particle inside the textile, because when you wash the textile, silver nano may be released to the environment. So the art is how to embed the silver nanoparticle or the cluster strongly to the textile so that it will not be going away while washing.
To integrating the silver-coated threads into the fabric. Nanotech is trendy and all, but clothing treated with silver can release some of that silver out into the environment when it's washed. Losing the silver particles from your exercise clothes is a double whammy. Not only would the gear lose its special anti-stench abilities, but the particles will also end up in our wastewater. This may be trouble because we don't know the long-term effects that these silver particles can have on the environment. A few studies have shown that silver can be harmful to fish, at least in a lab setting, and at high enough concentrations, they can be harmful to humans too.
You may have heard about the microplastic, the microplastic in the ocean, in the water, that released from the tea bag. When we drink a lot of tea, and most of the tea are instant tea that from the tea bag, and it was suspect that the tea bag released microplastic. So the question comes with the silver nano. How much is already in the environment?
Luckily, research shows that even incredibly small amounts of silver are effective against bacteria. The less silver that's put into
the silver nano, we don't use a lot silver nano. We just use a little bit. It's already effective to kill bacteria.
Garment, the less will leach out into the environment when it's washed and eventually thrown into a landfill. So the goal for researchers is to get as much bang for their silver buck as possible using smaller amounts that stick more tightly to garments. That will improve the anti-stink performance of your gym shorts, which means that you'll hopefully wash them less, which means you'll use less water, and less silver will leak out in the environment. Thanks for watching, folks, and thanks to Timothy Peterson for asking. If you've got chemistry questions, stick them in the comments or throw us a tweet. Let's see those gains, too. And before you head to the gym, remember to subscribe, share, and turn on notifications so we can see you again soon.
Okay. So silver is a very versatile material. It can be used not only to kill bacteria. Because of its conductivity, we can use silver nano as an ink, because we can print it. When it becomes ink, we can print it using inkjet printer. Make a electronic pattern on flexible surface like paper, plastic. You see, this is a silver ink. You can print it, and you can embed the silver nano particle around polyester to make a yarn, or thread that you can embed it onto the cloth to make the cloth conducting electricity. So it means you can put electronic circuit onto the flexible surface, not only paper, plastic. You can make it on garment, on textile. So it means electronic circuit could be not only on standard PCB, yeah, but now it can become on plastic, on flexible substrate, on paper, on cloth, yeah, on textile. Yeah. That open opportunity, a lot of opportunity for electronic device. Yeah. So I show you here that you can even do electronic circuit at home. Soft electronic circuit.
We present soft inkjet circuits, the first approach for rapid fabrication of soft circuits
This show you how
on a commodity inkjet printer.
Silver nano, onto paper, onto plastic, so that you can have a lot of possibility, to make electronic device, valuable one, by yourself.
Our technique supports multi-material printing of a variety of functional inks, including highly conductive silver nanoparticle ink, intrinsically stretchable conductive polymer ink, and an electrically isolated ink alongside graphical inks. These inks can be combined in a single printer, enabling various functionalities. For instance, these include printing circuits with an electrically isolated layer that leaves electrodes or pads for connection exposed, or printing circuits with a full-color art layer. For advanced mechanical properties of circuits, we can match these functional inks with a varied set of soft base materials. This enables inkjet printing circuits on highly stretchable substrates, on textile transfer films for printing e-textile circuits, on ultra-thin temporary tattoo films, and on thermoplastic materials for reshapeable circuits. Our versatile approach supports rapid prototyping of soft circuits in diverse application cases. For instance, fabrication of new stretchable input devices, inkjet printed textile circuits, printing of electronic skin tattoos, or inkjet printed e-accessory. We now present in detail the fabrication of our 4 example applications. Stretchable input device. For printing on stretchable TPU, photo paper is attached as a backing layer, including non-permanent glue. The sensor design is printed on the TPU film using silver nanoparticle ink. Once printed, the sample is cured in an electric oven. Wires for connection are attached. A paper box is folded. The sensor sheet is mounted. Connected to an Arduino Nano, the printed strain gauges capture spatial deformation input. E-textile circuit with full-color art layer. First, the design is printed on the textile transfer film in a single pass using silver and color inks. Then the sample is transferred onto the textile using a conventional iron. This step simultaneously heats and cures the conductive traces. By sewing with conductive yarn, the Arduino LilyPad microcontroller and LEDs are firmly adhered to the textile circuit and electrical connections are established. The printed circuit fully integrates with conventional e-textile electronic components. It features 2 LEDs that illuminate a full-color logo. Inkjet printed ultra-thin electronic skin tattoo. First, the color design of the temporary tattoo is printed on tattoo decal paper with color ink. A second pass prints circular electrodes with silver ink on top of the colored layer. The sample is heat cured. Electrical connections are added, and the temporary tattoo is transferred onto the user, with the electrodes exposed to the skin. Connected to an Arduino Nano, the tattoo is monitoring skin resistance, visualized in real time with a processing application. Thermoplastic inkjet printed e-bracelet. The color design is printed on shrink paper in a single pass using silver and color inks. The material is molded with a heat gun into the desired curved shape. This simultaneously heat cures the conductive traces. Electronic components are directly soldered onto the circuit. The device is connected to an Arduino Pro Nano. capacitive touch input controls the LED mounted on the wristband surface.
Yes, okay, yeah. You see that because silver nano has the very important property, yeah, called conductivity. Yeah, it can conduct electricity. Yeah, it can electrically conductive. Yeah, it can be electrically conductive. So because it's small and it can be embedded in textile, you can make a conductive thread out of the silver nano. Yeah, so you embed that coat the thread or yarn using silver nano. You can make that thread conductive. Once you make this conductive, you can make because you can use thread in textile. You can embroider, use embroidering the cross of garment using the thread. It means you can make this garment or textile electrical property. You can put electrical property or logical property, electronic into the garment or textile, which means you can make wearable electronics out of this capability. Yeah. So that's important. Yeah. When you want to connect electronic device, electronic part using the conductive thread. Yeah. For example, here, this is a sensor. The sensor on the smart glove. This is a touch sensor. When you touch something, it creates the force, and the force change to the electrical signal, and you use conductive thread to transfer the signal to the CPU here. And with this, the same. You connect electronic device using electronic thread, both the signal and also the electrical power to run the electronic device. You can use conductive thread. Then the conductive thread, very important part of the wearable electronics. And the guy behind this logo is the silver nano. You see how important it is. I show you the video that the electronic textile already commercialized.
So we
Here it is an exhibition.
The ID Tech X here with a 4-star roller. I love San Francisco, and this is awesome. So hello. So who are you?
Hi, I'm Jan Zimmermann. I'm head of the division of technical textiles at Forster Rohner.
So what are you looking at here? What is this technology?
This is an LED matrix display.
Can we look under it?
Yes, you can look under it. This is what it looks like.
Whoa.
It has almost 1,000 LEDs individually addressable.
That's
on
cool.
a purely textile circuit board.
And you see, if you look at you zoom in, the electronic circuit here connect each LED. They connect this with the conductive yarn, made of silver nano.
And it's flexible, it's washable, it's comfortable.
Really? Washable?
And yes, and you can display your own images or text on your t-shirt.
Text or numbers going on like this.
Yes.
This is so cool. So it's mostly about LED lights? Everything you do?
No, as a company, we produce functional fabrics that can be used to create textile sensors, proximity sensors, pressure sensors.
You see, conductive yarn here. Yeah. The
Like this?
very
Heatable
important
fabrics. Yeah,
element.
this is a heatable fabric.
You see here, conductive yarn.
But then one of our specialities is the LED technology, where we developed a technique to integrate LEDs into textile circuitry. And of course, being an embroidery company, we can then embellish the whole thing with nice designs.
Nice. What is
to-
this one?
This is also a matrix type configuration.
Every product they have the same pattern. They must have embroidered of embroidery of conductive thread onto the surface. You see.
On a leather-based fabric.
Leather.
Yes.
Oh, it feels really interesting. But is this durable?
Yes, this is washable in a household washing machine at 60 degrees. You can wash it 40 times without any problems.
Well,
And in this sense, it's a unique technology. You won't find this anywhere else.
No.
No.
So nobody can do this as nicely.
No, nobody can do this even nearly as nicely.
But is there any risk that something gets stuck and something, there's a little bump?
No, it's extremely robust. Bless you.
Yeah.
So as I said, you can put this in a washing machine with no problem. We put this into car seats. We put this into carpets. We put this into lingerie.
It needs to be on my jacket.
Yes.
I want this to be around like this and blink when I get an email.
As delicate as this looks, you can do anything with this. You don't
Really?
need to. You don't need to be afraid to destroy anything or short circuit the whole system.
Where's the power going through?
The power is going through a small cable leading to a USB power bank or a USB port.
Are you working with Omatex?
Yes, we work with Omatex. We also work with Interactiveware, who supply these kinds of components.
You see, yeah. Very.
Are you working with Omatex?
Yes, we work with Omatex. We also work with.
This one blend normal thread or yarn with the conductive thread and yarn.
Interactiveware, who supply these kinds of components.
So,
and we can use the same technology as you're filming. This is a product we built for a company called Carpet Light in Germany.
Beautiful.
This is a textile spotlight for professional filmmaking. This is used in Hollywood productions today.
So what is the advantage of having a flexible light like that?
Well, first let me show you the power of this thing. So you can tune the color temperature.
Whoa.
But you can also turn this up.
Yeah. Whoa, it's really bright.
Yeah. And this is lightweight. Yeah? If it falls down, it doesn't break. You can step on it.
It's beautiful.
Without having to worry.
Is this mass production then?
Yes.
Really?
Yeah.
What's the price?
The complete system, including a lot of professional lighting equipment that you need, like a diffuser and a mount to put it on a frame and all of that. So the complete box that you see down there is something like 4,000 euros.
4,000 euros, okay.
Yeah.
Is it guarantee? Is it gonna, it's like really good material, is not gonna break?
No, I mean this is, yeah.
That's really awesome. That's amazing. That's cool. So you already have lots of customers with that?
Yes. Well, it's not our product, no?
This
Carpet Light
Carpet
is the
Light.
company. And we supply the LED textile that's inside.
And then we look over here. What is this?
This is a heatable fabric for a jacket.
Nice.
Or over here you have ECG sensors for
ECG?
heart rate monitoring.
So this goes against your body?
Yes.
This part?
Yes. And it measures your heart rate.
Stuff like that is something you can manufacture quickly and cheaply?
Yes. So
Really?
we have production facilities in Switzerland and Romania and in China. And yeah, we have machines that turn out these fabrics in
By the-
seconds. By
in
the by the
seconds?
meter. Yeah.
Wow. And can we look at this one? Can I open it? Is it durable and
You
stuff?
see this the pattern here. the pattern here is connect the electricity to each LED. It's made of conductive yarn or conductive thread.
Let's open it like that. Can you take it off?
Sure.
And I guess it's too small for you, but
Yes, I can.
is there any chance that? Yeah, can you describe this? How does it work?
So this is a jacket by German brand Bogner, well-known ski wear brand.
Really? For ski?
And they commissioned us to develop LED textiles
Oh
to
my
build
God.
this jacket. And
So then you do nighttime
so
skiing with
as opposed to a lot of stuff that you see with lighting, this is not a prototype. This is a product, and
Really?
you see.
Because there's night skiing, there's different station, what's it called?
Well, this is
They have nighttime skiing, and this is just perfect for that.
Of course. Yeah. I mean, it's a fashion statement, right? It's a fashion piece. It's not that much a functional piece to make you visible on the slopes. It's to show the people that you're there.
That's so cool. How much it cost, do you know?
I don't know. No.
So,
But it's
is there any chance you can do LED colors?
You sweat anyway.
Because it'd be awesome if, let's say you ski, and if you go to the left, it's red. If you go to the right, it's blue. If you go straight, it's white. And then you do some kind of like light show.
Yes. So this is already in development in our labs to improve the system to full RGB. DMX controlled LEDs. Yeah.
Oh my God! If you have RGB, you start becoming a moving display.
Yes, exactly.
So there's a huge potential for this, right?
Yes, absolutely. Yeah. Primarily, the potential that we see is in interior decoration. There will be applications in fashion, but we don't believe that everybody will be running around with light-up clothing anytime soon.
I think they will.
But there will be or is a large market for interior decoration using lights.
Light up. It's like these people are gonna pay €1,000, no problem for that kind of. And how about what is the use for that? It's like Christmas
This
curtains.
is just a decorative curtain that you can use to improve your home.
Nice, and you can light it up. You have different intensities.
Yes.
And then you can light up your room a little bit from the curtains.
Yes.
Which is very
But it's
interesting.
it's more or less meant for decorating. So to create a mood with the light in the curtain and have this new haptics of.
So are you from
decorative lighting.
Germany or?
We're from Switzerland.
Switzerland, so Swiss.
Yes.
So is there any Swiss what's it called quality in this, or Swiss?
Of course.
What's it called? Swiss precision.
Yes, of course.
Where in Switzerland are you?
In the eastern part of Switzerland, in St. Gallen. That's
St.
what it's
Gallen.
called. It's near the Austrian border. Yeah.
All right, it's a good football team. All right, I'll check it out.
Okay. This company, I checked the company website. They are still running. Foster Roller. So I have finished the first one. So for the nanoceramic one, I think we continue next Saturday. So thank you very much for your attention. We see you again on next Thursday to continue on nanoceramic one. Bye bye. Thank you very much.